the properties of the Stokes operator. But you have to keep in view, this is the definition of the Stokes operator, or the description of the Stokes operator in the full space setting. In other words, that when you want to consider the Navier-Stokes equation in the entire domain actually. Okay, so it's like a fluid fills the entire universe, which is crazy. Okay. Alright, so what are the key properties of this Stokes operator? Okay. You know, one can prove that this operator A is self-adjoint, so that I can apply my theory of self-adjoint. Okay. And the A is non-negative in H. And another thing is, so this is one thing. The second thing that I would say, that A and the projection operator commutes actually. So they commute actually. So you can A and the projection operator commute. I'm going to use it a little bit later on actually. Okay, so if you have A operated onto pi of u, then this is same as, so that is that if you have A operated onto pi u, this is same as pi of AU. Okay, and you can get an interesting conclusion also, that if AU by definition is pi, so AU is pi of Laplace u, so I can write this as pi of pi Laplace u. Okay, maybe I write it here. So by commuting you mean that okay, A of pi of u is same as pi of AU, but if I substitute the value of AU into it, the definition of it into it, so it's going to be minus pi of Laplace u, but pi is a projection operator, so I can write this as minus Laplace u actually. Okay, so whenever A is operated onto say pi u in full space setting case, then you know it's going to give you minus Laplace u actually, and A and pi commute. Okay, so this is really the corollary to the fact that A and pi commute actually, that A operated onto pi u gives you the Laplace u. So this is the second condition. Okay, and probably the third and the important condition is, the third one here, okay, the third one is that if you consider the domain of A plus 1/2, this is equal to what you call V. Okay, this is equal to V, where V is what? H1 intersection H, and if you compute the AU, the inner product AUU, okay, you can also treat this as a duality product. This is going to be equal to what? The L2 norm of gradient of U for all U in the domain of A. Okay, so this is what is the key properties. Okay, let me rewrite this quickly here, that if omega is full space Rn, okay, then my H is the space from L2 that are divergence free. and my V is H1 intersection H, and the Stokes operator is AU equal to pi of negative pi of Laplace U. And another important fact is the domain of A plus I1 half is V, and the duality product, maybe the inner product of AU with U is equal to, what do you call, the gradient of U square for all U in the domain of A. Okay, so these are the two properties that I'm gonna require later on actually. Okay, probably I must say the domain of A is, okay, I must add that the domain of A is H intersection H2. Okay, so I have these key facts here because I'm going to use them again and again. Okay, I'm going to quote them again and again. So let's move to the next case when, you know, omega is not the full space, but say omega is torus actually. In other words, we are talking about the periodic boundary conditions. So consider the functional setting for the case when omega is really the torus. Okay. In other words, statistical. It's so you are talking about it. In other words, U is of the kind where if you move, say, L units in ith direction, you return back to the U. Okay. So in other words, okay. So if the U is a velocity, you may somehow interpret it, but it's better that I just keep myself, you know. So functional setting for, let me write it more explicitly, periodic domain. Okay, periodic domain. So in this case, I'm introducing, say, another L2. Okay, let's call this as L2 naught. This is the collection of U's. Yes, L2. This is the collection of U's. By the way, this torus can also be in 3, so I can put it Tn actually, which are square integrable with this domain, periodic domain, and with values in Rn such that the integral of the U with respect to dx over the entire domain is equal to 0. Okay? So you don't need divergence freeness here actually. So what you need is that, okay, integration of U over dx is 0. So it's a collection of such kind of space. What is H? Okay, H is in this case is going to be U from those L2 naught which are divergence free. Okay, and again V is H1 intersection H actually. Okay. All right. All right. Now let me give you what do you call a Stokes operator? So there are several details in this document. I'll share this document with you. You can read it from there. Actually, it's a paper by Jishla and Gaurav actually. Okay, and the book that I'm referring is the classical book by Timan on Navier-Stokes equation and numerical analysis. Okay, so I'll share that with you as well, so you can read the details from there. But I'm giving you the required key picture actually. So what would be the meaning of the Stokes operator in this situation? Okay, so the Stokes operator in this situation. So again, Stokes operator A is going to be an operator from domain of A onto H, okay, where the domain of A is really H intersection H2 on torus, okay, and AU in this case is not projection but simply Laplace, where the U is from the domain of A. Okay? So what are the facts about, in this case, Laplace operator? The fact is that A is a self-adjoint. Okay? The first thing is that A is self-adjoint, and A is positive, okay, unlike there A was non-negative in H. And the second thing is the domain of A1/2. So we know that if an operator is non-negative, the A1/2 operator makes sense actually. Okay, so the domain of A1/2 is V, and the A1/2 is basically gradient actually. Here you can treat A1/2 as gradient. Domain of A1/2 is V, and if you compute duality AUU, this is going to be equal to, if you compute say AUU, this is going to be equal to what you call norm of U square in V, okay, which is same as the gradient L2 norm of the gradient square for all U in the domain of A. Okay. So in case of what do you call torus, okay, you introduce another kind of a square integrable space whose integrals on the entire domains are 0, and then you choose the divergence free vector fields from that, and V is H1 intersection H, and this is the description of what do you call the Stokes operator. So in case of what do you call in case of the torus, the Stokes operator is defined in this manner actually. Okay, so it's pretty much important to keep these basic settings in head. Okay, so let me quickly write these things here. So if the omega is torus, okay, where n could be 2 and 3, okay, then what are the key things? The key thing is that we need to remember L2 naught, okay, which is the collection from L2 such that the integral of u of x dx over entire domain is 0, and then using this we define h, and then we define v in the similar manner, and the Stokes operator in this situation is minus what do you call Laplace u, and the domain of the Stokes operator is H intersection, what do you call H2? Okay, so these are probably some of the key facts. Like this identity is also valid in the periodic domain case actually. Okay. So we are done with the functional setting. What should be the next? Now let's apply this functional setting. There's one more thing actually. Okay. One more thing. Let me introduce the last thing in my functional setting, then I'll be position. So why we are doing all this struggle? Basically, we are doing all this, getting into all these details because, you know, we would like to talk about we would like to turn this Navier-Stokes equation into the standard form of the nonlinear evolution equation actually. Okay? So therefore all these things are important to keep. Obviously, with all this study that I just wrote here, there is a lot of mathematics behind it actually. Okay, but my objective is not to get into that mathematics into the detail actually. So I'm just throwing this superfluously to you actually, and I'll get into the details of only the important bits. Okay. Here are some important preliminaries. Okay, and these preliminaries are basically valid for all three situations where omega is in, say, Rn, or omega is equal to Rn, or omega is on torus actually. Okay, so whatever I am writing now is really valid for the case, then whatever with whatever domain you have actually. Okay, so consider a map B, small b, that goes like LP, that takes values from LP, W1Q cross, what do you call, L, R into R actually. And you define this as BUVW as a sum, okay, which is not difficult to recognize. So this is the sum I equal to 1 to 3 or 2, whatever, or maybe n. Okay, well, here the n means 2 and 3 actually, nothing else, not more than 2 and 3. So I equal to 1 to, what do you call, n, and this is equal to integral of over omega of the components ui partial vi by, it's a double sum, okay, it's a double sum, ij that goes from 1 to n. So ui partial vj by partial xj times wj dx. Okay, so this is what, okay. So B is a map from LP, from W1Q into R into LR into R, okay, and BUV is defined in this manner, okay. So it's a double sum on I and j, UI partial V, but we have to keep in view that U, V and W are components. So U has 3 components, U1, U2, U3, or U1, U2, and V has also 3 or 2 components like V1, V2, V3, and W has 3 components like W1, W2, W3, and you define the BUV in this manner actually. Okay, so what properties we can have about BUV? What are the key things that I can say and know about what do you call BUV? The first thing that I can say that it's okay. Maybe I should say something about PQR. Yes, I should say something about PQR. That the sum of 1 over P plus 1 over Q plus 1 over R is less than or equal to 1. Okay, so this is an important thing that I must say. Where PQR are any numbers between PQR are any numbers from 1 to plus infinity, so they can be anything. Okay. Is that B is trilinear, so it's like linear in each component and continuous actually. Okay, it's trilinear and continuous. And so the continuity is not difficult to show. What you can show is that, just show that this side is bounded actually. So if it is bounded, makes sense with taking u from here, v from here, and w from here, then you can show that it's continuity. Okay. So showing boundedness is not difficult. So this B is a continuous, also what do you call trilinear. And another thing that B satisfies is, alright, the next thing is this. I mean, what I would like to say is that recall something from function analysis course when we were kind of talking about say the Fourier transform operator actually. So we defined the Fourier transform operator as an operator with the domain, say the smooth space of smooth functions with a compact support, and the codomain as the space of square integrable functions actually. Okay. And then what we showed for that Fourier transform is that Fourier transform is linear and it's bounded actually. Okay. Then we had an abstract result which says that if you have a bounded map, so imagine you have a bounded map. I'm forgetting some of if I forget some of the assumptions, you can forgive me. Okay. So imagine if H is a Hilbert space and D is some dense subspace of this Hilbert space, and I have an operator, a linear bounded operator, that is defined from the dense subspace to the H actually, then what you can do, all such linear operators can be extended actually. Okay, so you can extend it to the entire space to an operator to an operator from H into what do you call H actually. So if this is linear and I guess bounded, and maybe there is some more assumptions, okay, but I think these are the two assumptions actually, but and maybe look, it's continuous actually, okay, it's continuous. Then continuous maps can be extended from a dense subspace to the full space actually. And we did this one example with what do you call the Fourier transform. I mean, if you remember, we defined the Fourier transform as the map, the space from as the map from space of smooth functions with a compact support into L2, and then due to this result we said that we can extend it to a map as from L2 to L2 that satisfies some identities actually. Okay, so we did it. So what I would like to do, let's think about the same case here actually. So B is a trilinear and continuous, and all these are, what do you call, you can treat them as a dense subspaces. So what you can do, dense subspaces, I'll say in a moment, is that what you can do, you can pick this map, and since it is trilinear and continuous, you can extend it to basically the entire space actually. And let me write that B can be extended and hence B can be extended to a bigger domain, which is V, okay, definition is same, cross E cross H into R, okay, into R, so you can extend it like that. This is extended. Where V is what? So we know the V in each one of these situations. E is the domain of the A, okay? So the E denotes the domain of this Stokes operator actually, okay? And H is, as we have defined it, you know, in case of Rn and say in case of the domain being periodic actually, okay? So the B can be extended to this space actually. So what we can show, the second important property we can show about B, I mean if you're interested you can see all this stuff and all these proofs from the Timam actually. I'll upload the chapter of the Timam and you can read it from there. But I'm just, you know, just putting the key thing, and you can already see that, you know, even to begin with, you know, the Navier-Stokes equation in abstract setting, you need a lot of what you call preliminaries and preparation actually. Okay, you know, one can teach and learn an entire course on Navier-Stokes equation actually. Okay, so it's a big topic. Okay, and the B and second thing is that B satisfies an estimate actually. Okay, so what are the estimates for B? That for all U from V and V from say V from E, okay, V from E and phi from H, there is an estimate for BU phi that goes like this, okay, and this is equal to square root of 2. You can put a constant here, C actually, but you know, the constant here is sharp, so let's just write this. U